Okay, this is the second lesson on gases, ideal gases, and the ideal gas law. An ideal gas is a hypothetical gas with the following attributes. The particles move randomly in straight lines. Collisions are elastic, meaning no loss of kinetic energy after a collision. The particle size is insignificant in comparison to the size of the container, and there are no attractive forces between the particles. So we use this to help us understand how real gases behave. So let's do a question. The Goodyear blimp has a volume of about 2.5 times 10 to the 7 liters. The temperature of the gas is usually about 261 kelvins and a pressure of about 112 kilopascals. What would be the amount of helium gas in the blimp? So our volume is 2.5 times 10 to the 7 liters. The temperature of the gas is 261 kelvins. The pressure is 112 kilopascals. And we want to find the amount. So because our pressure is in kilopascals, our R is 8.314 kilopascal liter mole Kelvin. So we're going to solve for N. So PV divided by TR is N. So pressure 112 times volume divided by temperature. Make sure it's in Kelvin. And our R value. So this is 1.29 times 10 to the 6 moles. So there's 1.3 million moles of helium gas in the blimp. And if we multiply that by the molar mass of helium, we would know that there is 5.2 times 10 to the 6 grams, or 5,200 kilograms of helium in the Goodyear blimp. All right, determine the density of 1 mole of pure nitrogen gas at SATP. So standard ambient temperature and pressure. So the temperature is 25 degrees or 298 Kelvin. The pressure is 100 kPa. We know we've got 1 mole. We want to figure out the density. Well, there's no density formula in this. However, we do know that moles are equal to mass divided by molar mass. And we do know that density is mass per unit volume. So if we substitute in mass over molar mass and then rearrange this, we will end up with mass over volume. So this is density. So now plug in your values. So the pressure is 100 kPa. The molar mass of N nitrogen gas, N2, is 28.02 grams per mole. And the temperature is 298. And then our R value, 8.314 kPa liter atmosphere moles. So density then is equal to, when you put all these numbers in your calculator, 1.13, and the units that are left did I put? That should be Kelvin, not atmospheres. Don't know what I was thinking there. Kelvins cancel. So now we're left with the units grams per liter. So the density of nitrogen gas at SATP is 1.13 grams per liter. All right, determine the molar mass of 1.965 grams of gas having a volume of 1 liter at STP. So STP means 273 Kelvin, because it's 0 degrees Celsius, and the pressure is 101.325 kPa. So PV equals TRN. Substitute in the formula mass over molar mass. Rearrange to solve for molar mass and plug in our values. So the temperature is 273. Our value, that's supposed to be a decimal. And the mass, 1.965 grams. And then pressure, 101.325 times the volume of 1 liter. So the molar mass of our gas is 44.02 grams per mole. That happens to be the molar mass of carbon dioxide. Determine the mass of sodium azide required to inflate a car's airbag to 67 liters at 32 degrees Celsius and a pressure of 105 kilopascals. Well, the gas that inflates inside of an airbag is nitrogen gas. So this sounds like a stoichiometry question to me. Ooh, I'm actually giddy. 2 sodium nitrides will decompose into this. There's 3 steps to inflating your airbag and having the products become safe. And this is the one step that actually produces the gas. So we have 67 liters of nitrogen gas, 32 degrees Celsius, which is 305 Kelvin. So that's volume, that's temperature. Pressure is 105. We know our value, so we can find the moles of nitrogen gas, use the mole ratio to figure out the moles of sodium azide, and the molar mass of sodium azide is 65.03 grams per mole. So, step 1, isolate the formula for the moles. Plug in your values. So pressure, 105 kilopascals, times the volume, divide by the temperature, times the R value. And that will give us 2.774 moles of nitrogen gas. Now we need to convert that to moles of sodium azide, and the mole ratio is 2 moles of NaN3 to 3 moles of N2. So we end up with 1.8495 moles of sodium azide. Multiply that by the molar mass, and it's approximately 120 grams of sodium azide, because we took 1.8495 and we multiplied it by 65.03. So you can do a lot of calculations using the ideal gas law. So you can solve for, you can do a stoichiometry kind of question like this one. You can find the density of a gas, the molar mass of a gas, which allows you to identify it. Or you can do just straight up, what is this one variable, once I know the other 4. I did mention that once you have the ideal gas law, you can solve for any of the other gas laws. So if you read a question, you've got a pressure, you've got a volume, you've got a new volume, what's the pressure? I know that my temperature and my moles are kept constant. And my formula involves only P and V. So P1V1 is equal to P2V2. If I have a volume at a certain temperature, I change the temperature and want to know the other volume, I know that I need my formula to only include volume and temperature. So if I take pressure, move it to the other side, that means it now divides. And I move my temperature to the other side, so now it divides. But this is now a constant, so V1 over T1 equals V2 over T2. So if you read the question and you notice what the information is, like pressure, temperature, and then a new temperature, what's the pressure? You know the letters of the formula that you need. So you take a look at the ideal gas law and you rearrange it so it just has those letters in it, those variables. So I want to get P and T only in the equation. So I'm going to divide both sides by V and then divide both sides by T. So V cancels. T cancels on that side, so I have P over T is equal to Rn over V, which is a constant. So P1 over T1 is equal to P2 over T2. So really, the only gas law you really need to memorize is the ideal gas law. PV equals TRN.